So here's a problem. You're flipping a fair coin over and over, and the first 5 times all turn out to be heads. If you were to place a bet, should you bet on the next time resulting in a head or a tail? Back in my university years, one day one of my parents' friends came to visit. He heard I was a math major, so he asked me this question. I tried explaining the concept of independent events and how the previous results are irrelevant, and that if anything, seeing 5 heads in a row should make us want to bet on heads next, because by definition, it's impossible to have a perfectly fair coin in real life. If the coin ends up not being perfectly fair, getting 5 heads in a row would suggest that it's biased towards heads. The family friend made a face of disapproval throughout the entire explanation. I was a bit puzzled by his reaction. It felt like he had more to say, like he wanted to refute me but didn't find the words. So I tried to figure out why it's such an instinctual response for people to disagree with the independent event argument. It wasn't until recently that I made the connection to a couple of laws people refer to when talking about games of chances. There's the law of averages, which says future events tend to balance out past events to align with the theoretical values. And then there's the law of large numbers, which says the larger the sample size of an event, the closer the experimental values should align with the theoretical ones. These 2 laws sound similar, don't they? But they mean completely different things mathematically. And only one is applicable in the case of repeatedly flipping a fair coin. Suppose we are to flip a fair coin 10 times in total. Without any further information, the theoretical value for the results should be about half and half of those flips, which is 5 heads and 5 tails. Say we then do the first 5 flips and just happen to obtain 5 heads. This is the same setup we had at the beginning of the video. Now let's take a look at what would happen if we apply each of the 2 laws here. With the law of averages, the next 5 flips should balance out the results so far to match the theoretical value of 5 heads and 5 tails. Now, there will be some variance since this is a game of chance, but on average, we should be getting 5 consecutive tails by the time we finish all 10 flips. With the law of large numbers, however, each flip still has the standard chance of 50% heads and 50% tails. So the next 5 flips on average would give 2.5 heads and 2.5 tails. Again, there's some variance since this is a game of chance, plus the fact that we can't physically get half a tail as a result of a coin flip. Say we end up with 3 heads and 2 tails, which is one of the most likely outcomes. That brings us to a total of 8 heads and 2 tails for the 10 flips, which is 80% heads and 20% tails. This is still quite far from the theoretical values of 50-50, but a bit closer than the 100% heads we started out with for the first 5 flips. Tag on another 10 flips and we'll get an average of 65% heads and 35% tails. If we repeat this process, our running average will tend to keep getting closer to the 50-50, even if the occasional long streaks of heads show up again. So which law is right here for the case of flipping coins? If you've been paying attention, you probably noticed that only one of them is compatible with the concept of independent events. The coin doesn't have a way of knowing what results it produced already, so it has no way of deliberately balancing out previous deviations from the theoretical average. Only the law of large numbers respects this characteristic of coin flipping. The later coin flips push the running average closer to the theoretical, not by acts of balancing previous deviations or having more than average of the opposite cases, but by diluting it, making it an increasingly small deviation compared to the total. Whew, math makes sense again. Now I wonder what other famous probability fallacies or paradoxes I should dig into next. Let me know in the comments below, and until next time, stay curious.